so our second speaker of the morning is Anthony Bloch from the University of Michigan. And his title is not there.
So there's
we'll see
the title.
Toda flows and the generalized Flaschka map. Okay.
Okay. So yeah, so thank you very much for the invitation to be here. It's great to be here and to celebrate Michael's birthday. This is the talk, and I'll come back to that in a little bit. So let me just start off with a recent picture of Michael. That's actually Toda on the right, a colleague of mine who's related to some of this work in the talk. Anyway, it's been a great pleasure to know Michael over the years. This was just a couple of months ago, but I've known Michael for a long time. I was just trying to think the first time I met or saw him, I think, was when he gave a talk on solitons at the University of Michigan. It was about the stability of solitons, and I remember it well, actually, and it was related to a couple of things that are still of interest to me, both integrable systems and stability and asymptotic stability. And this talk is going to touch on those things, as well as some more recent work that I've done on the Toda lattice and its dispersionless limit. And in fact, interestingly enough, it does touch a little bit on the talk we just saw. There's going to be a lattice in it, and there'll also be a hexagon, I think mainly coincidentally, but maybe not, you never know. So, so that's the sort of history of how I first met Michael. I think I first met Michael's family, actually, at a tennis and swim club in Ann Arbor. And I think it was actually Michael's birthday, if I'm not mistaken, but I don't remember exactly what birthday it was, but certainly it was quite a long time ago. So anyway, it's been a great pleasure to be associated with Michael, both personally and academically over the years. And I'll say a little bit about some of the work that I was lucky enough to do with Michael as well at the beginning of the talk. So the talk today, as I said, is about the Toda flows, and in particular the Toda lattice. As I'll show you in a moment, if you're not familiar with this, the Toda lattice is a lattice. It's a one-dimensional lattice of particles on the line and interacting under an exponential potential. It's a beautiful example of an integrable system, and it's given rise to all sorts of interesting generalizations, some of which I want to discuss today. So I'm going to begin by discussing a little bit dispersion and radiation-induced instability, which relates to work that I've done with Michael. And this is related, in fact, to the Toda lattice flows, and to some extent my work on it was inspired by it, because the Toda lattice, at least the finite Toda lattice, which I'll talk about today, is both a Hamiltonian system, but it's a system that also exhibits intrinsic dissipation and asymptotic stability, if you like. So they come together in a rather interesting way, and it's related to the particular metrics that you find in the system, and I'll discuss these various metrics, and they have a rather interesting and beautiful geometry. It's also related to action angle variables and something called the Brzezinski condition, which shows that the natural geometry in the system, so like many integrable systems, it flows on a coadjoint or an adjoint orbit, if you like, but it's a coadjoint orbit of a solvable group, and those are nice things, and in particular they're kind of flat in some sense, and since they're flat, you get these nice asymptotic dynamics. Are related to what's called the Flaschka map, and also the dispersionless Toda, which is an infinite generalization of this, which lies on the diffeomorphism group of, say, the sphere or the annulus. So let's see, does this work? Yeah. So here, so I'm going to summarize a few of these flows, and I'll try and describe some more of the relationships between them in detail as we go along. So here, so here is the Toda lattice in a rather general form. So you can think of X here as being a symmetric matrix, if you like, but there are all sorts of interesting Lie algebraic generalizations, essentially due to work of Bertram Constant. I won't take too much about the Lie algebraic geometry except towards the end if I have time. So you can think of it as a symmetric matrix, or in particular a tridiagonal matrix. That's the simplest case where you have a nearest neighbor interaction. X is symmetric. This is just the skew symmetric part of X in the skew symmetric upper diagonal decomposition. And this gives rise to a rather beautiful flow. This is the generalized Toda flow, and it's an integrable system. You can show it's in lax pair form. It has all sorts of integrals, and you can show it's explicitly solvable. The tridiagonal case, which I'll discuss today, is a little simpler, but nonetheless, many of the same features carry on from the tridiagonal case to the full symmetric matrix case, and as I said, to many Lie algebraic generalizations. This is related to a so-called double bracket flow. So this is in general a gradient flow, in fact, with respect to a particular metric. But in fact, in the case of the Toda lattice, these coincide, and you get a very beautiful sort of coming together of these Hamiltonian and gradient flows that I'll show. And here's another representation of it in terms of projection matrices, which I'll mention briefly later. And so the study of sort of dispersionless flows, or flows that flow on orbits in finite infinite dimensions, leads to all sorts of interesting equations. For example, if you extend this is some recent work that I did to loop groups. Instead of taking a finite dimensional group, you look at loop groups, you can get a whole class of interesting PDEs, which I won't touch on too much today, but it is related to it. For example, the heat equation turns out to be a special case of this. There's a flow that looks like this. It also arises from a flow with respect to a suitable metric on the loop group, and there's a natural Kähler structure associated with it. And one thing I do want to talk about today is the so-called dispersionless Toda flow, which is sort of related to this double bracket flow I just showed you earlier. But here you just think of Poisson brackets as opposed to ordinary brackets. So you can think of this in some sense as being the classical flow, and that is the quantum, if you like. And then you can put these things together. So you can think of Hamiltonian flows and gradient-like flows. This is so we call this double bracket dissipation. And this is related, in fact, to some of the work that I did with Michael earlier. And I want to say a little bit about that first. So this is related to radiation damping. So as I said, one of the things I've always been interested in, aside from integrable systems, is stability. And one of the things that I did with Jerry Marsden was look at stability of systems using the so-called energy momentum method, which Michael used essentially to prove the stability of solitons. And the idea is you can use the energy and momentum of many mechanical systems to prove stability via Lyapunov methods. And the question is, if the energy and momentum fail, the combination of energy and momentum fails to give you stability, is the system unstable or not? That's a reasonable question, because if you have a Lyapunov function, as you know, if you have a Lyapunov function, things are stable. If your Lyapunov function fails to give you stability, you don't really know whether it's unstable or not. There might be another Lyapunov function lurking out there somewhere. And one of the things that we were able to show for a certain class of systems with Jerry Marsden is if you add a tiny little bit of dissipation to the system, you can show that the system is unstable, in fact, spectrally unstable. So if I have a system where the natural Lyapunov function fails to show stability, you can show with the tiniest little bit of dissipation, natural physical dissipation, the system truly is unstable. So that takes you out of the class of Hamiltonian systems, but nonetheless, for all practical purposes, shows you the system is unstable. And one of the things we wanted to look at was, can you extend this to the Hamiltonian setting? So, for example, if the Lyapunov function fails to be showed the stability, is the system really unstable? And Michael suggested looking at radiation stability, in fact. So the question is, if you have, for example, if instead of having dissipation, you have the system connected to a wave field, for example, or some sort of radiation field, is it still possible that the system becomes unstable? And that's one of the things we looked at in various ways. And there's this rather beautiful model that I think Michael introduced me to, the Lamb model, which goes back to the origin of physics. So I think the paper was originally in 1905, if I'm not mistaken, and was one of the first models for an electron in a field. So you have an oscillator physically coupled to a string, and the vibrations of the oscillator transmit waves into the string and are carried off to infinity. So this is a rather beautiful pre-quantum mechanical model with all sorts of interesting properties. So it's very simple to write down, so I thought I would just do it. So this is the Lamb model. So you have Wxt, the displacement of the string, with mass density rho and tension T, and we have a singular mass density at the end of the string. And then I'm interested in how waves are carried off from the particle along the string. So here it is. I have this little oscillator, a little mass connected to the string. And it's a simple sort of linear model. So here is the wave equation. This is my finite oscillator model, and it's connected to the string by this little boundary condition here. So this T is the tension of the string, and this is the derivative or slope of the string. And then they're connected by Q of T is equal to W of 0T. And it's a rather wonderful little model. So this is what Wx0 means. This is a jump discontinuity of the slope of the string. So you can think of yourself as just plucking the string, and you can show by a rather simple little bit of analysis that the model actually reduces to a system of this type here, actually. It's just really, you can just do this using the Laplace transform. You can show, if you look at the dynamics, reduce it to the dynamics of the oscillator, and there's the dynamics of the oscillator plus a dissipation term. So in fact, the string even though it's an infinite dimensional Hamiltonian system, really acts, if you just look at the oscillator, as a damping term. So, and this, in fact, you can think of as a Rayleigh dissipation term that you'd get from finite dynamics. So it's a rather beautiful model that illustrates how being connected to a wave field can induce actual damping on a little finite dimensional system. So this is a lovely model. As I say, it's related to quantum mechanics, but it has all sorts of other interesting generalizations. This is the work that we were looking at originally, and as I said, partly with Toda, whose photograph appeared earlier. So if you look, for example, at a linear system of this type here, so it's just a second-order system, if you like, but with a gyroscopic term, and that's kind of the important term. So here, M is a positive definite matrix, lambda is a symmetric matrix that could be indefinite, and S is a skew-symmetric matrix. So you can think of it as describing rotations, if you like, and I'll show you a picture of that in a moment. So this is a system which is Hamiltonian like that, but with a slightly more complicated Poisson bracket than the usual bracket. So you can induce the gyroscopic terms by the skew-symmetric term in the Poisson bracket. And in fact, this you can show is a normal form for certain mechanical systems. So in fact, it's the normal system, the normal form of a mechanical system which is invariant under the action of an abelian group. So it's actually rather general, and it's related to sort of a general analysis of stability problems that I mentioned earlier. So this is the dissipation-induced instability result that I mentioned earlier in the abelian setting, that if you just take an equation of this form here, and I add a little bit of dissipation to the system, then if the system has lambda being indefinite as opposed to definite, and then a little bit of dissipation for epsilon, however small, you would at least get one pair of eigenvalues moving into the right half plane. And this is the kind of, and so the question that I originally looked at with Michael is if instead of having a little bit of dissipation like that, if you added in radiation, if you connected the system to a field, does it still go unstable? And in fact, you can show that it does. So the physical models, you can think of various physical models that fit into the setting. So one thing is you can think of a rotating plate with springs that looks like that, where you have one of the strings being a sort of physical spring and the other unphysical, sort of negative definite, if you like. And you can sort of generalize it to a whole class of systems that look like this, a wave equation, this gyroscopic system that I just showed you, and a sort of coupling term that looks exactly like that wave coupling term that I showed you earlier from the Lamb model. So if you like, it's a generalization of that lovely little Lamb model to this gyroscopic setting. And again, you can show that it reduces to a sort of system in gyroscopic form with a damping like this. And and if you like, the simplest physical system that you could think of like this is a spherical pendulum. So as you know, if you take a pendulum, of course, it's stable if you hold it downwards. If you hold it upwards, it can be unstable. It's still Hamiltonian, but in some sense, if you just connect it to if you spin it, it's a rather cute model actually. If you take that inverted pendulum and you spin it around at its base, of course it's unstable, but if you spin it fast enough, it can actually stabilize. That's gyroscopic stabilization. On the other hand, if you connect it to a wave field, if you like, by magnetizing it or something like that, you can show it becomes unstable, or if there's the slightest bit of dissipation. So that's sort of the physical manifestation of that. So anyway, that was sort of some fun work. And what I want to talk about today mainly, though, is how you connect Hamiltonian and dissipative dynamics through the Toda lattice. Just before I do that, though, let me just mention, as I mentioned, that you can sort of couple Hamiltonian and dissipative dynamics in many ways. One of the interesting things is through what is called Metroplastic Systems, which were developed by Phil Morrison, who's a physicist at Texas. But in any case, you can actually think of systems which have both Poisson brackets and sort of a metric, and you connect systems with a Poisson bracket and a metric, you get all sorts of interesting dynamics that combines dissipative and Hamiltonian dynamics. So you can think of the system essentially as being of this form here. I have a Hamiltonian piece and I have a Riemannian piece, and you look at how the dynamics fits together, and you can think of one of the pieces as being the sort of dissipative piece and the other is the Hamiltonian. But in the Toda lattice, they come together in this rather interesting way. So let me get now to the Toda lattice. So by the way, I told you it's about 9:30, just to keep things in. Or yeah, 9. Okay, so this is the Toda lattice. So this is a rather beautiful system, actually. So as I said, it describes an interaction of particles in the line. There's the finite dimensional version, which is originally due to Jürgen Moser. And there are various versions. There's a periodic version. You can look at it on the whole line. But as I said, it actually is on a lattice. And this is the Hamiltonian of the system. It's simply a bunch of particles in the line interacting under this particular exponential potential. And you can write down the Hamilton's equations of motion just using the canonical form. So they look like this. And the boundary conditions, which are due to Moser, is this convention here. I simply said e to the x0 minus x1 equals e to the xn minus xn plus 1 equals 0, which corresponds to putting the 0th particle at minus infinity and the n plus 1th particle at plus infinity. All right, so it's essentially sort of stretching off the particle to infinity, if you like. And it has a wonderful structure that you can see in lots of different ways. The key result, in some sense, was due to Flaschka in 1974, which was just to observe that if you make this change of variables here, so I said ak equal to e to the xk minus xk plus 1, essentially, and bk equal to minus yk over 2, the equations then take this form over here, and you can rewrite them in terms of a lax pair representation. And this is sort of the key to the whole analysis in some sense. So they take this form, L dot equals B bracket L. L here is this tridiagonal matrix, and that's simply because the matrix is nearest, at least the dynamics is nearest neighbor. And B is the skew symmetric part of L. And one can show the system is integrable in various ways. As I said, it generalizes to other systems on Lie algebras and so on. The way to see it's integrable is to look at the traces of the powers of L. So the integrals, in fact, so how do you show a system is integrable? Well, as you know, if it's a 2n-dimensional system, you need essentially n integrals of motion. And in this case, the n integrals of motion simply come from the traces of the powers of L. So this is in fact, this is an isospectral system. That follows from this, rather simply from the lax pair form. That means it preserves the spectrum. And equivalent to preserving the spectrum is you can show the traces of the powers of L are conserved. And that's enough, in fact, to prove the system is integrable. For the full symmetric system, if this is a fuller matrix, you need some other integrals, but in this case, it's enough. And there's some other interesting dynamics that goes along with this, which follows from the double bracket structure. So as I mentioned, this double bracket structure is sort of dissipative, but in the Toda setting, in fact, both of these come together in a rather interesting way. And you can see that as follows. So if you take n to be the matrix diagonal 1, 2, 3 through to n, you can check that this form over here, so let's see, so this matrix, this flow, L dot equals B bracket L, is in fact exactly this flow, L dot equals L bracket N, where you choose the matrix N to be the matrix diagonal 1, 2, 3 through to N. Okay, and you can just check that L bracket N is equal to minus B. You get the right thing. And so this is just an observation, but the nice thing about it is this in fact enables you to show that the flow is also a gradient flow, and it's a gradient flow of the function trace Ln with respect to the so-called normal metric. And I'll show you how that works in a moment. So the flow is both sort of gradient and Hamiltonian in an interesting way. And the way you can think of it in various ways. In some sense, you can think of it as you've taken, again, this infinite system and made it finite. You've compactified it in some sense. It's non-compact, so for a normal integrable Hamiltonian system, the level sets of the integrals is normally a torus, but in this case, since it's non-compact, the level set's a bunch of lines, and you have this flow on the lines. Okay, so let me just show you, give you a simulation of what it looks like. So here's the total. So here's the four-dimensional case. This is the Hamiltonian in this case. The equations of motion look like this. You can check the sums of the BI's along the diagonal is equal to a constant. And trace Ln in this case is just equal to B2. So that's the gradient function, if you like. And you can check that it decreases along the flow. And this is the flow. I guess it's a little hard to see here. But what you can check is, so this is just the diagonal entries. And what you can check is if you look at the diagonal entries, what happens actually is they sort themselves and eventually flow asymptotically to the eigenvalues. And this relates to a rather beautiful observation of Bill Symes. You showed if you took the Toda lattice flow, if you start off with any initial configuration, what happens is that the flow diagonalizes, and it flows eventually to the set of eigenvalues sorted, actually. So it's a rather nice thing, and it's sort of easy to see in a way from the system. So first of all, if you look back here, this is it's an isospectral system, but it's easiest to see in this form. So it's isospectral. It means it conserves the eigenvalues. N is a diagonal matrix, so if you want the eigenvalue, the equilibria of the system, the only possible equilibria are where L and N commute. All right, so the only possible solution, which is an equilibrium, is when L and N commute. N is diagonal, therefore L is diagonal. So it flows to a diagonal, and since it's isospectral, the only possibility is that you flow to the eigenvalues. So it's a rather nice thing. It's a way of actually computing the eigenvalues of a symmetric matrix. And in fact, you can show that it's related, in fact, to the famous QR algorithm. So if you go onto MATLAB, for example, and you find the eigenvalues of a matrix, it actually does use the QR algorithm. And this is, if you like, a continuous version of the QR algorithm, which computes the eigenvalues of a symmetric matrix. So it's actually a rather beautiful thing. And if you just discretize it, you can see the QR algorithm pops out of it in a rather natural way. So that's the sort of diagonal flow. So as I said, it's sort of related in some sense to the integrability and to action angle variables. And it turns out that if you sort of follow along that sort of reasoning, the sort of natural action angle variables turn out to be the eigenvalues, since they're conserved along the flow. So those are the actions in some sense. And the angle variables, in this case, just turn out to be the top components of the normalized eigenvectors, in fact. So I've written those here as R. And you can rewrite the flow, in fact, in terms of these normalized eigenvectors, which conserve these lambdas. So you can, in fact, rewrite this flow in this rather nice form here, which is also double bracket. So P here is equal to R transpose, where R is this vector of the top components of the normalized eigenvalues. And the flow is also in double bracket form, sort of, again, for interesting reasons. And as I show, it does turn out that it's related to a convex polytope. And in fact, the polytope in this case is a hexagon. So this is the hexagon that we just saw some pictures of in the last talk. But I don't think it's related. But anyway, so here is a hexagon. And so this hexagon is actually the moment polytope. So what it is in this case, so the flow, and in fact, I don't know how much time I'm going to have to talk about the general situation, but there's this beautiful theorem called the convexity of the moment map, which is due to Atiyah and Gilliman and Sternberg, which says if you have the action of a torus on a symplectic manifold, the image of the moment map is a convex polytope. And the simplest manifestation of this is the so-called Scherr-Horn theorem, which is, again, is just a theorem in linear algebra, which says if you take a Hermitian matrix and you project onto the diagonal entries lie in the convex hull of the symmetric group acting on the eigenvalues. So if I take the eigenvalues of a symmetric matrix, they're all real, and I act on them with the symmetric groups, I take all possible permutations of this vector, I get a whole bunch of points in space. If I take their convex hull, I get a convex polytope. And the Scherr theorem, in fact, says that the vector of diagonal entries of that Hermitian matrix lies inside that convex polytope. And the Horn theorem is sort of the reverse direction. It says if you give me any diagonal matrix and any set of eigenvalues, I can produce for you such a Hermitian matrix. I can relate a Hermitian matrix to it. So it's onto in some sense. So for the Toda flow, what you can do is, so remember, it's a flow on symmetric matrices, and I'm interested in the diagonals. So if I look at the diagonals of this flow, those diagonals just flow inside a polytope. Okay, that's the Scherr-Horn polytope. So you can check that the flows flow inside this polytope, and in fact, you can show that this polytope for the Toda lattice is homeomorphic to the set of tridiagonal matrices, and it's actually diffeomorphic up to the edges. So the flow on the tridiagonal matrices of Toda actually is literally on that polytope, and just one of these vertices corresponds to the stable configuration. So for example, in the 3×3 case, you have the 3 permutations of the eigenvalues, so 1, 2, 3, 2, 3, 1, and so on. And what happens is you'll say your flow, say from the stable, say from an unstable edge down to a stable edge. And so that's sort of easy to look at the stability analysis using the gradient function that I showed you earlier. So that's how the polytope appears, and in general, or at least how the hexagon appears, and in general, you'll get a convex polytope. And as I said, this is true for both general symmetric matrices, the general symmetric Toda flow, and many Lie algebraic generalizations of it. So there are other generalizations. So in the last 10, 15 minutes, I'll sort of say something about some generalizations of this picture. So this is the basic picture, but the same sort of thing repeats itself. You get this nice interplay between Hamiltonian and gradient-like flows. Here's another interesting case of this. This is the so-called Toda rigid body. So the Hamiltonian for the Toda equations is just trace L squared. So there's no inertia matrix. You can actually generalize it to a rigid body equation where you have a non-trivial inertia matrix, and then you get an interesting generalization that looks like this, and it also has rather sort of beautiful asymptotic properties. So let me just say a little bit about the metric structure, and then I'll generalize it to the infinite setting. So how is this a gradient flow? So as I said, it's Hamiltonian. What's the gradient structure? So it's sort of interesting to see that. So let's say in general, you can think again of symmetric matrices if you like, or you can think of a semi-simple Lie algebra. I have a flow that looks like this, L dot equals L bracket n, and I want to know how is this a gradient flow? Okay, well, there's a very simple way of seeing this. So this is a flow on an adjoint orbit, if you can think of it. Since it's an isospectral flow, the flow is basically by conjugation, all right? So it's theta transpose Q theta. That's what it flows on. All right, so you can ask, how do I write a metric on an orbit like that? And it's very closely related to the standard symplectic form on adjoint orbits. So first of all, to get a metric, right, I need a tangent vector. And tangent vectors just turn out to be brackets, L bracket x and L bracket y. And that's just basically the infinitesimal form of the adjoint action, right? If I have theta transpose Q theta as my orbit, and I replace theta by e to the tx, right, and I differentiate with respect to t, I get a bracket, right? So those are tangent vectors, L bracket x and L bracket y, and I need a way of pairing them together. And the way to pair them together is like this. So what this little analysis means is I simply pair, so you could just take trace Lx and trace Lx, Ly, and that's a metric actually. It's called the induced metric. But that's the wrong metric for us actually. The metric that you want is what's called the normal metric. And that what you do there is basically you just take the part of x that does not commute with L. So you break up x into a piece that's in the part of it that commutes with L and a part that does not commute with L. So that's the image of ad L and its complement. And I take that pairing, because basically I don't care about the part of x that commutes with L. It's a sort of a natural thing to do, right? Because L bracket x is going to be 0 if it commutes. So I just pair them together like this, and this is the right metric, okay? It's called the normal metric, and it's a rather lovely metric. And if I just carry out the natural gradient computation, take that metric, take the gradient function, this is this little computation, I'll just skip the details, you get this form over here. And so that's the right metric that gives you this double bracket form. And in fact, if you look, it's rather interesting, if you look at Atiyah's original paper on convexity of the moment map, there's a little remark at the end that talks about these three different metrics on an orbit. There are these three natural metrics. There's the induced metric, which I just mentioned, the trace together. There's the Kähler metric, since any orbit is both a symplectic manifold and a Kähler manifold, so there's a natural Kähler metric. And there's this normal metric, and it turns out that the right metric in this case is the normal metric, and you can compute with it exactly. So you can take the Kähler metric and the induced metric, and you also get, of course, a gradient flow. But the one that produces Toda and gives you this nice explicit form is this one. And in fact, the Kähler metric, you can't actually write down the gradient flow explicitly. So if you look at the papers on convexity, they all deal with the Kähler metric, which is a great metric, but you can't actually write down the flow explicitly except in some special cases. So for example, if you're on the Grassmannian or a projective space where everything's degenerate, then the normal and the Kähler metrics coincide. So that's the metric. And this is, I guess, more or less what I said. So there are these three natural metrics, the induced metric, the Kähler metric, and the normal metric, and they're related in a rather precise fashion, which you can find in Atiyah's paper. Okay, so the last part of the talk, I sort of want to say something about how you generalize this to PDEs. So, and again, there are a number of different generalizations, but the natural one, at least for us, was the group of diffeomorphisms. So if I simply take the group of diffeomorphisms of the annulus, so you can think of it, if you like, as how a fluid works, for example. You think of the Euler equation. This goes back to Arnold, right? You can think of a fluid as a group of diffeomorphisms of some space. In any case, here I take this group S diff of A, of area, but not necessarily orientation diffeomorphisms of the annulus. And the Lie algebra of this case is the system is the algebra of divergence-free vector fields tangent to the boundary, right? So if you take a divergence-free vector field on the annulus, it'll produce for you naturally an area-preserving diffeomorphism. And these guys themselves are Hamiltonian. They're Hamiltonian with respect to the normal metric, d zeta, at least the normal symplectic form d zeta wedge d theta. And their Hamiltonian functions, x of z theta, satisfy this set of boundary conditions. And you can just look at those flows. So you can identify the Lie algebra G with the algebra of Poisson, the Poisson algebra of functions obeying these boundary conditions. And many of the things I've just discussed you can generalize to this setting. So in particular, I want an adjoint orbit, a sort of a natural version of conjugation. And that, in this case, for the diffeomorphism group, just turns out to be composition. So the adjoint orbit in this case is I just take a function f on the annulus, and I compose it with an area-preserving diffeomorphism, f of g. So that, in fact, is an adjoint orbit of the group of area-preserving diffeomorphisms, all right, just composition. And with that, you can do all the sorts of things that I've just mentioned. So you can write down the Hamiltonian flow as I discussed there. You can write down a tangent vector, and just by using the same sort of reasoning that I just gave you, a tangent vector in this case, instead of being a bracket, is now a Poisson bracket. And just about everything I've said goes through where you simply replace regular brackets by Poisson brackets, and you get the same sort of story, which is kind of cute. So the function f, so if you want a function trace f, it's just, instead of the trace, you take the integral of f dz d theta. I can define a natural pairing between functions, which again is just the integral. I can write down a natural Lie Poisson bracket of the system, and I can write down a natural normal metric. And so the normal metric in this case is pretty much the same thing. So this is just boundary stuff you can ignore, but basically tangent vectors now are sort of Poisson brackets instead of regular matrix brackets. Excuse me. And then and the normal metric in this case is exactly the same. You just pair these Poisson brackets together in the same sort of way as I paired the matrix brackets together, and you get a rather interesting PDE that comes out of it. So for example, I could look at the Hamiltonian flow of a function, and in this case it just turns out to be x dot equals x bracket z. So if I'm thinking of the annulus here, I think of coordinates on the annulus as being z and theta. So theta is a natural angle variable going around the annulus, and z just is a sort of radial vector. So that's my annulus, and these are my functions. And so xt is equal to x bracket z. That's the Hamiltonian flow. And then I can also look at the double bracket flow, which looks like this. So xt is equal to x bracket z. So that's the double bracket flow on the annulus. And that's actually a very interesting PDE in its own right. And I want to relate it to Toda in a second. But in fact, it's an equation of Monge-Ampere type, one can check. And the general properties of this equation are still not completely understood, but it's a rather beautiful equation. And it has all sorts of nice properties that are related to its gradient structure. But in fact, in a particular case, it's Hamiltonian. And I want to show you what that is. So yeah, so I won't go through the details of the proof. Again, you can show its gradient. But I want to relate it to Toda. And so again, one of the things that's important with this equation, so remember in the finite dimensional case of the Toda lattice, you had the traces of the powers of L conserved, since it's a matrix flow, an isospectral flow. In this case, it turns out the analog is that the moments of the x to the k are conserved. So I have x dot equals x bracket something. The moments of the function are conserved. So there are infinitely many integrals, if you like, which is good for integrability in infinite dimensions. So I should say, just as a sort of caveat here, this is completely formal in some sense. So these equations are generally of hyperbolic type, so they can exhibit shocks, in fact. So you don't know about infinite existence in general, although you can say something, but I won't worry too much about that. But one has to worry, of course, since it's a PDE, about long-time existence. Let me relate it, though, to the Toda lattice. So how is it related to the Toda lattice? But again, there's a rather nice way to see this. So how would you get a PDE out of the Toda lattice anyway? Well, as I said, the Toda lattice is just a set of particles on the line back to the lattice. So if you wanted to get a PDE out of it in a natural physical way, you just take the lattice spacing to 0, right? So the lattice spacing is epsilon. I just look at the limit of these things as epsilon goes to 0. And the way to see this is I just put n equal to epsilon z here, and let epsilon tend to 0. And if you do that, this is the set of equations you get. It's a pair of equations, a hyperbolic set of PDEs, and we call it the dispersionless limit of the Toda lattice. And in fact, it's closely related to the KdV equation. In fact, it's a sort of highly nonlinear dispersive limit of Toda, and the KdV equation basically just ignores some of the nonlinear terms that appear in this system. And this turns out also to be integrable, but it will exhibit shocks in general. The nice thing about KdV, of course, is you get long time existence in many settings. Here, unless the initial data is very nice, you get finite time blow up. But nonetheless, in some sense, it's simpler than the KdV, and the geometry just follows, very much from the finite dimensional settings, since you take such a sort of simple limit. But it's related, in fact, to the double bracket equations, and I'll just show you that. So as I said, this is a quasi-linear hyperbolic system called the dispersionless Toda lattice. There are again an infinite number of integrals. So instead of having traces of L to the P, in this case you have integrals, and the integrals look like this in this case. So the integrals are u of z plus v of z e to the 2 pi I theta plus v of z e to the minus 2 pi I theta. And this just enables me to relate this PDE back to this double bracket. So remember there's the double bracket. So let me sort of just end with this, I guess. So I'll probably have to. So the way you think about this is there's a sort of rather beautiful infinite dimensional version of the tridiagonal matrix. So what's an infinite dimensional version of a tridiagonal matrix? Well, you just think of a Fourier series. So I have my function u of z theta, where this is on the annulus, and I expand my function in a Fourier series. So what's the tridiagonal version of a Fourier series? Well, I just take the 0th component, which is u of z, and the first two coefficients in the Fourier series. So the way I think of this infinite dimensional tridiagonal matrix is I think of it as sort of described by the diagonals. So that the 0th component of the Fourier series is the diagonal of the matrix. The first component of the Fourier series are the upper and lower diagonals, and that's my tridiagonal matrix. And it turns out if you take this function x of z theta and you write it like this, let's see, so if you think about it, actually, this thing is just my tridiagonal matrix, and it actually gives Toda. So this is just the Hamiltonian structure. So let me just skip that. But so if I write down the double bracket equation, x dot equals x bracket z, I take x to be this tridiagonal matrix that I just described to you, and I work this out. So I simply take x dot equals x bracket z. This is the Poisson bracket. With this tridiagonal matrix, so to speak, I end up exactly with these equations. So this set of PDEs is exactly a sort of tridiagonal flow on these tridiagonal infinite dimensional matrices, and it has all the nice properties that you might expect, up to sort of blow up, etc. Of the finite dimensional setting. So it's like a gradient-like flow. It'll sort as long as the initial data is nice, which basically means monotone decreasing. And there's even an infinite dimensional hexagon, or polytope, if you like. You simply take the convex hull of the set of all functions with fixed moments. So the correspondence of fixed eigenvalues is to take trace integral x to the p fixed, for p going up to infinity. So in fact, there's a beautiful sort of version of the Scherr-Horn polytope that you can see in this setting as well. So I think I should probably sort of stop at that point. The last thing I just wanted to show, and I'll just sort of leave this as a final point, and this is sort of some recent work that I did with Tudor, Ratio, and Francois Gay-Balmaz, is you could ask, is it possible to introduce global Darboux coordinates on the co-adjoint orbit of a Lie group? And in fact, it's possible, so you can get global action angle. So action angle variables in general are a local thing, but in fact here you can do it globally because the group you're looking at is basically a co-adjoint orbit of a lower triangular group. That gives you the symmetric matrices. So this whole thing, even though generally you only get local action angle coordinates, here you can get a rather beautiful set of global action angle coordinates, and it's related to some sort of famous work among some people. Pujansky is a guy who worked on solvable Lie groups, and he talked a lot about sort of global action angle coordinates. Anyway, it turns out you can use Pujansky's work to get global action angle coordinates rather for this system, and that turns out to be exactly related to the Flaschka map that I showed you earlier. So this map from tridiagonal matrices to Toda and back is an example of this sort of global action angle coordinate setting for solvable Lie groups. So that's sort of part of the reason there's this very nice geometry that you get here. Okay, so I'll stop there. Thank you.
All right. Are there questions?
Thanks. Coming back to the Lamb model at
Oh,
the
right.
beginning of the talk.
Yeah.
So energy dissipates to infinity, but
Yeah.
but it seems that energy cannot come in from infinity and excite a previously quiescent particle. Does that have to do with the boundary conditions? Why can't, the usual question about?
Yeah, no, so I think it is the boundary conditions, right? So things dissipate out to infinity. So yeah, if there was some sort of, if there was some sort of reflection at infinity, of course it could come back in.
So what are the?
A finite energy solution.
Suppose
Yeah.
but suppose, for example, you have a system and it's, the ball is bouncing around.
Yeah.
And then it dissipates out. It hasn't gotten to infinity yet, but
Yes.
some of it has disappeared. Then you run the picture backwards. Can you not run the picture backwards?
Yes, you could run the picture backwards, I guess, if you took t to minus t.
Yes.
So, yeah, so I guess you could have something coming in from it. I suppose you're right, it's a Hamiltonian system. You could have something coming in from infinity, I think.
So
Yeah, so
how do you rule that out? And more generally, you have Hamiltonian systems which are also gradient-like.
Yes.
So there is a preferred direction in which they evolve. What's with that?
right. Well, so there is so that's right. Well, it goes down. So there is a downhill direction. So it's so you have this trace of this functional. It evolves on a particular adjoint orbit. So it does. So you're right. You could run it backwards. I think it all depends on the initial conditions. You could go backwards. There is a preferred direction. I could run it in any. So if I take that polytope, for example, I could run it from one point to another simply by changing the sign of the initial condition or changing the sign of the Hamiltonian. But there is a preferred direction. It depends on the initial data.
So if you run it backward, you're changing the initial data, and therefore you're changing the preferred direction.
That's what I would claim.
That solves that one. How about back to the Lamb model?
So I don't quite know how to set this up physically. I think you could run things if you change time, I think you could run things from infinity back to the initial particle, I believe. I don't exactly know how to do that. Yeah.
Let me comment on this. So in principle, it's true. You can take initial condition, which is nice.
Yeah.
And you wait for a million years, then you go backward in time, and you see the spring start moving again.
Right, I think so.
You can see it numerically as well.
Yeah.
But you don't see it in nature.
True.
And the reason is that once it spreads to infinity, arbitrary small error that you do at infinity will create a new initial condition that cannot come back coherently and create this oscillation. That's hard to prove, but that's what happens.
Yeah.
Eddie.
Just a quick comment about the Lamb model, because I was at Michigan when this happened. So yeah, what it happens is in the example he described, the string is at 0 initially, but if you put finite energy, H1 energy, for example, in the string, yeah, for a long-time behavior is the same, we can prove that, but for a while it can gain energy from the string, it can oscillate harder, but eventually dissipates to infinity, which is exactly what Avi Sofer has just said. So that's how I understood at that time the Lamb model. But coming back to my understanding of this talk is that you are exploiting the gradient flow to do long-time dynamics on this Hamiltonian system.
Correct.
Now, how often these Hamiltonian systems do coincide with gradient flows, and do you have a method to see which ones do and which ones don't?
Yeah, so I don't. So the answer is I don't. It doesn't seem to happen very often. So as I said, I mean, there are a number of ingredients that you want. In particular, you want the system to be the level sets of the integral to be non-compact, and you'd probably like the system to be integrable. So this infinite dimensional system that I just showed you works, and analogs like this. But the other sort of natural Hamiltonian systems you might think of don't look like this. For example, we've looked at the Calogero-Moser model, for example, and those don't. So as far as I know, it's restricted to sort of Toda lattice systems and their analogs, basically. So at least finite at least Toda systems of finite type and their analogs.
And as you pointed out, Toda is closely related to KdV, so I was going to say that, well, for KdV, of course, there is a kind of sorting that goes on, which is the solitons of different amplitudes, which separate linearly because of their different speeds, and I was wondering if there might be some kind of double bracket structure underlying that.
Yeah, no, we've thought about that. So a conjecture. So for example, you can relate the KdV flows to flows on type. So you need to find. So certainly there's a sorting behavior, and you see that in many systems. But the thing is it actually gradient? That's the thing, is to actually come up with the metric. And so we thought, so for the KdV equation, you can realize it on Teichmuller space, for example, and there's a metric that looks a little similar to that. So that's something we have been looking at recently, in fact. So I think it's entirely possible that with the right space and the right metric, it could be, but we haven't found it. So and I guess as a related answer to your question, there are systems that behave very similarly to this, but actually showing that they're exactly graded. That's a very tight condition, and that seems to be very restrictive. But I wouldn't be surprised if it were true for KdV, but I don't know that.
A related model to the Toda lattice is, I guess, the symmetric discrete Burger's equation.
Yeah.
Is there a framework for that equation that can be described in this?
Yeah, so it's very close. I'm not sure. So if you, if you go back to this, this is, how did that happen? What did happen, actually? Something bad happened. Anyway, it doesn't really matter. So if you look at those, so I just wanted to, so I just want to show the PDE again. Yeah, so those are pretty close to the Burger's equations, actually. If you look at them, they're almost like a two-dimensional Burger's equation. So that does have this gradient equation. I'm not quite sure about the discrete Burger equation itself. It's a good question. I've never actually thought about that specifically. But I sort of think of this basically as two copies of like coupled Burger's equations. They really are very close. Yeah.